So let's look at the wave equation. And so let's call it optical waves and the wave equation. You can write the wave equation as follows. It's a differential equation, del squared E equals 1 over c squared d squared E by dt squared. So what you have is you have a spatial derivative on the left-hand side of the equation, and you have a temporal derivative on the right-hand side of the equation. And in this, so let's just do that. I'll just call this space, and I call this time. And E is called the electric field. C is called the speed of light. C, speed of light. And that is equal to 3 times 10 to the 8 meters per second. So this tells you how quickly the electric field propagates through empty space. So this is in vacuum. It turns out that in a medium, if you, for example, have light propagating in air or through water, then we denote EU as the speed of light in a medium is given by the following. So we have it turns out that there's a relationship that looks like this: C in vacuum divided by C in medium is given by N, where N is the refractive index of the medium. Sorry, this is C and this is U, refractive index of the medium. So what this tells you is that, for example, water has a refractive index of greater than 1.3 or something like this. And so if you multiply, if you take 3 times 10 to the 8 as the vacuum speed, meters per second, then in water it will be 1.3 times slower. And so only in vacuum do you get this velocity, this speed. In fact, in air, the refractive index is so close to 1 that we just say it's equivalent to the speed in the vacuum, right? So you have in the lecture notes a few different materials. You have air has a refractive index of 1, glass 1.5 to 1.7, so it significantly slows down the speed. Water has 1.3. Immersion oil, which is often used, you put a drop of immersion oil onto a microscope objective. We will talk about that later. And that immersion oil, through which we often image in inverted microscopes, has a refractive index of about 1.5. And so there we are. Now the first thing we would like to look at is the concept of plane waves. And so in Cartesian coordinates, you can write plane waves as follows. The electric field E is given by Ex times I, where this is a unit vector, Ey times J plus Ez times K. And so you can rewrite the wave equation in these Cartesian coordinates. You can write one for each component. So let's write this for the x component. So you might have d squared Ex by dx squared plus d squared Ex. So this is still the same component, but now in the y direction. Plus d squared Ex by dz squared. And that is given now by 1 over u squared, d squared Ex by dt squared. So now this is in vacuum, this equation here, but if you replace c with u, you get the corresponding wave equation in a medium of refractive index n, where n is c divided by u. Okay, so the point here is that you have analogous components now also for Ey, so you get the same thing for Ey and also for Ez. Same equations. You get 3 equations for all these components. But let's now assume that we have a wave, the electric field of which travels along the z direction. So a plane wave that looks like this. So you have plane waves. This is lambda, we notice, in space, and it's traveling along the z direction like that. So there are no field variations along x, and there are no field variations along y. So these terms here, they will be 0, and only this term remains. So you get a much simpler equation. We can now drop the coordinates Ex, Ey, and so on, because there's only one component. So it's the field along this thing here. So we would then write this equation as, so it's traveling along z. We can write this equation as d squared E by dz squared. So where we've dropped the Ez, because it doesn't really make a difference, because everything varies along the z direction anyway. And then you can work out the solution for this. You know this, how to solve this partial differential equation. You know that the solution is E of zt is equal to E naught cosine kz minus omega t. And so, so this is just to make this clear, this is little k, and you can also write that as E naught cosine 2 pi of kappa z plus nu t. Okay, so let's see what that is. So E naught is the electric field amplitude. Z is, of course, the propagation direction. T is time. Omega is the angular frequency. In radians per second. And that is given by 2 pi times nu, where nu is the frequency of the light wave in hertz. And then we have k is equal to 2 pi times kappa, and that is called the angular wave number. And kappa is equal to is equal to 1 over lambda. Lambda is the wavelength of light, and that is equal to the wave number. And it has units of per meter. Okay, so this It's very simple to understand. So essentially you get a sinusoidal oscillation of the electric field amplitude, and it varies along Z with a frequency, a spatial frequency of k, so once per lambda. So if lambda is very, very small, then the amplitude will very quickly as a function of z, and if lambda is large, then it will be more slowly as a function of z. So this essentially tells you how the electric field varies in space, and this term here tells you how quickly it varies in time. So if the light wave comes across, and so I'm looking at the field at a particular point, then it will vary at a frequency nu in time. And if I, on the other hand, take a snapshot in time and look at the electric field distribution in space, then in space I will get a modulation that's modulated as kappa times z, like this. And just to be sure, u, the precise name of it is called the phase velocity, because it tells you how quickly the phase is moving through space, and the phase is, this is called the phase of the light. Okay, so let's look at some plane waves. So you remember plane waves propagate like this along z, right? So this is lambda, and so you can see that if I take a cross section through this, then the electric field E may vary as a function of z it will change as 1 over lambda, right, the spatial frequency. And so you can equally look in time. So so this would be E of t z at t equals 0, for example. And I could also, so this is taking at a particular time point, what is the electric field distribution in space? It will have this sinusoidal modulation. And then similarly, I can look in time. Let's just pick a point. Let's take this point, and let's see what happens at that point here, at that z0. What happens at that point? If I wait at that point, then in time, the field at that point may change something like this, right? So that's called the wavelength lambda in space, and in time that is called the period tau, and that is given by 1 over nu. Okay, and this lambda is given by 1 over kappa, as you can see. So you have the spatial modulation of the field, and you have the temporal modulation of the field. And of course, one feeds the other, right? Because of this equation. That is how they're related to one another. And anywhere you take this cross section across this plane wave, you will see this modulation in space. It doesn't depend on this position in x and y. The field will vary according to this, and it will change according to this solution here. That is what a plane wave is that propagates along z. In the next part, we can look at a plane wave in 3 dimensions. We are not really it's not really that important for this course that you require the full detail, so I'll just show you this from the lecture notes again. So, but you can get the idea. So if I have an electric field propagating in an arbitrary direction, right? Then we have to use vector quantities. So if I want to know, let's suppose I want to know what is the field. Let's take a point in space. Let's take this point. What is the electric field at that point, right? So you can write that. So at a point x, y, z at a particular time t, the field will be E0 cosine k dot r minus omega t. So that temporal variation is exactly the same. So what you get these planes of equal phase, of constant phase. This is what a plane wave means, except now rather than traveling along one of the Cartesian coordinates, along z, it's now arbitrary, right? So the way you can describe these planes of constant phase is by first of all noting that point has coordinates r. So r is, so it will have, I mean, this is going to be hard to draw. I'll try. So it may have coordinates something like that. So it will be along z like this, along x like that, and along y something like that. So it will have coordinates xi and yj, zk, right? So that gives you r, right? And then the k vector, so this is the wave vector, as we now it has vectorial quantities. I mean, it's because it can be in any direction. It will have component kx times I, ky times j, plus kz times k. The magnitude of k, the wave vector, is just given by kx squared plus ky squared plus kz squared, and the square root of that. And so the scalar product here, the dot product k dot r, leads to a set of planes, as shown here, which are spaced at lambda. So this distance is just lambda. So this vector, dot product with that vector, gives you the components across which, the planes across which the phase is constant. So spaced again at lambda. So you can try this out. You will see that this works. You can try, collapsing this for a wave that goes halfway between x and y, but has got no z component, or just along y or just along x, and you see that this dot product, when you do it, makes sense. It gives you it should reduce to the previous result if you collapse it to z, let's say, and so that then is the same idea. So we have this k dot r. The reason why I've done this is because it leads to something slightly simpler. You can imagine, right, that if I have different r's around here, then at different distances from the origin, the phase will change in this plane wave, right? That makes sense. Think about that statement, see whether you understand it when you look at this diagram. So that's why we need the dot product to get these planes. I will come back to this when we go to the the other important wave, which are spherical waves. So before I do that, I want to make our lives easier. It is very difficult to work with cosines and sines, and you need lots of maths to look at how waves superimpose and add up and stuff like that. It's far easier to deal with complex quantities. The math becomes much easier, and so I will briefly recap what the complex notation is. As much as you need in this course. So the Euler representation looks something like that. E to the I theta is given by cos theta, you know this, plus I sine theta. And of course, this is the real part of this complex number, and this is the imaginary part. And you can draw this on a circle like this, where theta is this angle here. We draw, this is I, this is +1, this is -1, and this is minus I. So the imaginary part is this distance of this vector along the y-axis, and the real part is this part, so it's the cosine of this angle here, and this length here is r. So if I have r times e to the I theta, then this is what this means. So the length of the vector here is r, and this angle is theta. The real part of this complex number is the projection onto the x-axis. The imaginary part is the projection on the y-axis. Now this is often called a phasor because you can rotate this phasor in time, and then the projection of this, as you may have seen, if you move it in space, gives you a perfect sine wave. So this is related, of course, to what we've just been talking about. Okay, so with that in mind, let's just look at a few important quantities. So let's suppose I have a complex number z is equal to r times e to the I, let's call this now theta, like that. Let's look at theta equals pi. Then you get e to the I pi would be this angle going to here, so you would just get this direction. If this is pi is 180 degrees, so you go over to this side, you flip over the phasor from here, flip it to this direction, rotate it by 180 degrees, or by pi, and so this is equal to -1. And of course, I can do the same thing by rotating by minus pi, so that is equal to e to the minus pi. That's the same thing. If I rotate this original vector here from to go to here, so I'm sorry, the way I've drawn this circle to have a radius of 1, right? And so r equals 1 in this particular case. Otherwise, this is multiplied by r, right? So if let's make r equals 1 for this diagram. And so if I have e to the plus minus I pi over 2, which would be flipping this by 90 degrees, then what you get is you get just the plus or minus I for this, right? So there's no complex, there's no real part left, it's only the imaginary part. And then finally, e to the I 2 pi is equal to just 1, right? Because that's rotating this vector starting off here just by 2 pi, and there we go. And then importantly, if I want to get the for a number z equals r to the e I phi, I theta, then to get the length of this vector, all I need to do is to multiply the complex number by its complex conjugate and take the square root. And you can try that again yourself to see that that's really true. And so now we can take our plane wave, which we had written as E is equal to E naught cosine of k dot r, these are vector quantities, minus omega t. The complex notation would look as such. We have E, but the tilde just denotes that these are complex amplitudes now, is equal to e to the I k dot r minus omega t. And of course, that is equal to E naught cos k r minus omega t, k dot r cos omega t, plus I sine k dot r minus omega t, which looks very similar to the original wave, the ones that we've been dealing with so far, except for that imaginary part that you have in there. But you therefore realize that E is simply the real part of our complex amplitude E. And the reason why we bother with this is actually dealing with these type of quantities is very much easier mathematically than dealing with these quantities. Or sorry, with these quantities here. Okay, and with that I will go to the last bit of this lecture, and then we're done, which is great, namely what a spherical wave looks like. So a spherical wave, as we said, here the phase is constant in a spherical volume at a constant distance from the origin where the emitter is sitting, where a point emitter is sitting. So you have your point emitter, it emits these spherical waves, and at a constant r, any r, the phase is constant across this. And you can, the actual equation for this looks as this. So we write this now in complex format, is E naught over r times exponent I kr minus omega t. Now, you may now wonder, right, because that looks very much like what we said, let me just see whether I find the piece of paper that I drew this on for you. Oh no, we have this here. This looks suspiciously similar to this equation here that we had for a plane wave in 3 dimensions, right? So we have, you remember, so this is just another way of saying this is just a complex representation, but of course there's a cos kr minus omega t term in there. So a cos kr minus omega t, which looks exactly the same, except here, this is a dot product, so you have vectorial quantities, and here this is just a normal product of 2 scalars because it doesn't matter in which direction you go with r, for the same distance r, the phase is constant. And so that makes this equation much simpler. So it looks, to all purposes, like this plane wave in 3 dimensions, except it's much simpler because you don't have to bother with this. And so there's another term in there, which is this r, E naught over r. And so this r is really just to think about the flux that you have, the field flux. If you think about this, as you go out, these spheres get larger and larger, and so the actual field amplitude will be shared over a bigger area, and so the field amplitude will diminish, and that's what this takes care of. In fact, the field amplitude diminishes by r, and the intensity goes as r squared, right? So it goes with area and therefore with distance squared. So we will talk about that in the next lecture. So with that, I think we just wrap up by saying, I mean, I just wanted to bring this point home, why this dot product. You know, if I have a plane wave and I take an origin like this, then of course it matters whether I go along in this direction with k or whether I go along in this direction, because the phase is changing more slowly, let's say in this direction, than it would change in this direction, right, along z, if this is z, for example, as we looked at, and therefore it makes a big difference, right, on whether you write this as a scalar or as a dot product for the plane waves. That's the difference. Whereas here, for the same distance from the origin, you get the constant phase. Right. Finally, and importantly, because actually this is the last bit, it's only going to take a minute, but it's very important. The intensity of light is given by I is equal to E times E star. So it is actually, if we deal with complex numbers, so in fact, I should say this should be a tilde because it's to make sure that we know it's a complex quantity, and And so this would be the same, but because it's unambiguous in all cases, we just drop it and we just say, we just write this as we go along as this, understanding that the physical quantity is the real part of the complex number. But as far as the math is concerned, it doesn't matter. In the end, we work out intensities, and when we work out intensities, the complex stuff comes out anyway, and you get a real number. And that's exactly the same as what you would have got if you went through pages and pages of math with the real quantities only. Okay. It's this thing, it's because the intensity of light, which is actually what you measure and what you detect with your camera or with your eye, because it is proportional to the square of the amplitude, E, that you get interference effects, constructive and destructive interference. And that's what then ultimately leads to diffraction and you know, what is important when we add up the light waves that form the image later on. So then that just finally some useful numbers. These are numbers you should really remember because you need them all the time, and you know, on back of the envelope calculations you will need them in exam questions. It's just useful to have that so you can check whether the answers you get are sensible. So the speed of light is 3 × 10⁸ meters per second. The wavelength, the visible wavelength range, these are the colors that you see by eye, between 400, that's the blue spectral region, to 700, that's the red spectral region. And in the green, so this is where the sunlight peaks, the frequency of light is about 10⁻⁵ hertz. So that's an enormously big number. And so what this means is that if you look at a point, a wave comes past, then the electric field oscillation in time at that point will change amplitude 10⁻⁵ times per second. So incredibly quickly. And too fast for any detector really to detect. So you can't resolve these individual cycles. You always see the average of many, many, many cycles. And no detector has yet been found that can resolve individual light cycles. The wavelength, 500 nanometers, is sort of a ballpark figure. That's half a micrometer. 1 micrometer, 10⁻⁶ meter. So half of that is 500 nanometer. That's in the green spectral region. Just for comparison, a human hair has a size of about 50 micrometers. 50 × 10⁻⁶, so that's 5 × 10⁻⁵, and you compare that to half a micron. So we are down in the 10⁻⁷ range. So it's about 200 times smaller than a human hair, or of that order, roughly. And with that, I will finish this lecture, and I'm looking forward to seeing you again next time. Thank you.